All right, silly people, here's the situation. We have a um, particle of some kind that's has an angular momentum of gamma 1 J1 plus gamma 2 J2, um, and it's in a state of Jm J1 J2. Um, right. So, and then we're meant to find the expectation values of all of the Cartesian components of the angular momentum vector, right? So, and we're supposed to use this big equation up top, which basically relates the expectation value for any component of a vector operator to a expectation value of vector operator dotted with the angular momentum vector divided by h bar squared j plus 1, and then multiplied by pretty much an expectation value of a Cartesian component of angular momentum, right? Um, so let's, first thing you want to do is you want to re-represent mu as a linear combination of j and j prime, which I'll define as being the total angular momentum and kind of a truncated angular momentum, respectively. And then you want to, so just solve for j1 here. So that'll be j minus j2. Plug this in over here, so you'll have j prime equals j minus 2j2. Solve for j2 as being j minus j prime over 2. And then plug that in over here. You get j1 equals j minus j prime over 2, which evaluates to j plus j prime over 2. Now that we have these, we can plug them into mu, and we'll have a rewritten expression. Gamma 1 over 2, and then inside here you'll have j plus j prime, and then gamma 2 over 2, j minus j prime, right in there. I'm going to resolve this, collecting the terms differently. I want the angular momentum vectors to be the leading terms, and the gammas to be inside the parentheses. So it'll be gamma 1 minus gamma 2 there. And then we can look at the Q component of mu, which will be defined as Jm, J1, M1, J dot mu times the ket Jm, J1, J2 divided by h bar squared j plus 1, j1, j2, jq, j1, j2. Right. So it doesn't matter which component of the angular momentum vector you're looking at, it's going to have this term in each of them. So let's go ahead and just figure out what that term is before we do anything else. So looking at j dot mu now, it's going to be j squared over 2 times gamma 1 plus gamma 2, and then j dot j prime over 2 gamma 1 minus gamma 2. And then you can simplify the j dot j prime stuff as being as being j1 squared minus j2 squared, because that's how we defined j prime over 2, gamma 1 minus gamma 2. So we're really just taking the expectation value of j squared, j1 squared, and j2 squared, and getting the appropriate coefficients for each of them. So for j1 squared, that's a known expectation value, or rather, it has known eigenvalues, right? Um, which will be h bar squared times j plus 1. Similarly, for j1 squared, you'll get h bar squared j1 plus 1. And for j2 squared, you'll get h bar squared j2 plus 1. Makes sense. So looking at the entire expectation value now, we'll bring out a 1 over h bar squared j plus 1 over here. I'm evaluating this. You'll have gamma 1 plus gamma 2 over 2 times h bar squared j plus 1. Then you'll have a gamma 1 minus gamma 2 over 2 term, which is multiplied by h bar squared j1 plus 1 minus h bar squared j2 plus 1. Simplifying a bit, all the h bar squared stuffs will cancel out. You'll have gamma 1 plus gamma 2 over 2, and then that gets canceled out there, and then you'll have gamma 1 minus gamma 2 over 2, and then times this stuff in here, which will now be j1 plus 1 minus j2 plus 1 all over j times j plus 1. That should do it. So the mu q, the q component of the expectation value, will be equal to this stuff, which I'm just going to copy down. Equal to this stuff times, we still have the J1, J2, JQ stuff to worry about. For X, you can see that I'm just going to call this big thing alpha for now. You'll have alpha times J1, J2, JX, J1, J2. But there is a relation between JX, JY and the raising and lowering operators. That being J plus minus equals JX plus or minus IJY, which you can solve for JX and JY as being JX equals J plus J minus over 2, and J minus being J plus minus J minus over 2I, and that's supposed to be JY. So we got those lined up. We can look at the expectation value of X will be alpha J1, J2, J plus minus J minus. You'll have a factor of 2 out here, J1 J2. And I'm not even going to talk about the eigenvalues of these operators, um, because as it turns out, um, you'll end up with a um, you'll have one that is multiplied by j1, j2 plus 1, and you'll have a couple of vectors that are multiplied by j1, j2 minus 1, both of which will be 0. Um, so don't even worry about ux. Similarly for mu y, um, when you plug in the relationship between jy and the raising and lowering operators, that was supposed to be a plus up there, but it doesn't matter. It's supposed to be 2i, so j plus minus j minus. Again, you'll have the same two dot products of eigenvectors, which will both evaluate to 0. So this is also 0, right? But mu z will be this factor times j1, j2, jz, j1, j2. Jz has an eigenvalue, but it doesn't change the eigenvector. That eigenvalue being mh bar. So this inner product will evaluate to 1, and so you'll just have mh bar times that big factor. So now we can write it all out as being, and by write it all out, I mean go and copy down the thing, mh bar times that. And I think that was the form that Shankar wanted you to solve it in. So there you go. The next two parts of this problem involve some kind of numbers that I don't really care about, so I'm just going to leave it there with your analytic solution. All right.